Hey everyone, hope everything is going good with you. So in today's video, I want to do another application-based video on Coulomb's law and just apply the general formula we learned and then apply some algebra with it along with vectors, and I'll be presenting that in this video. So let's get started. So number 5, calculate the net electrostatic force on charge 2 due to the presence of charge 1 and charge 3. Okay, if you don't know what the net electrostatic force is, don't worry about it. I'll explain it in a minute, but it's essentially it's like a vector sum. Okay, so if I have two vectors and I add them either numerically or graphically, I'll get a resulting vector, right? That's what the net electrostatic force is. It's like the net vector or the net force. So I'll explain it more in detail when I start presenting the problem. So let's begin. So here's it graphically. So here's the x-axis. Here's charge 1 with the magnitude negative 12 microcoulombs, charge 2 with the magnitude negative 18 microcoulombs, and charge 3 with the magnitude 24 microcoulombs. Alright, so charge 1 and charge 2 are separated by a distance of about 4.1 meters, and charge 2 and charge 3 are separated by about 3.8 meters. So the net force is the total force, right? So if I wanted to combine two vectors, right, or I wanted to combine two forces, right, in this case, the net force is just the sum of those two forces, right, in terms of their vectors. That's how it works. So, okay, let's start explaining this out. So here, shown in purple or pink, the force on charge 2 due to the presence of charge 3, okay? Q2 or charge 2 is going to feel force that's going to attract it towards Q3, right? It's going to be pulled in the positive x direction towards the right, as shown by the arrow which is pointing in the right direction. That's the vector. And for Q, or for Q2, due to the presence of charge 1, so the force on charge 2 due to the presence of charge 1 represented by the blue arrow, because of Q1's magnitude, but sign being negative, obviously it's a negative charge, right? So what's going to happen is Q2 is going to feel force that's going to repel it, right? It's going to go away from Q1. It's not going to go towards it. It's going to go away. So in this case, that would be in the positive x direction or towards the right, right? So as we can see, the net force will essentially be the addition of this this pink vector and this blue vector. It's the force on charge 2 due to the presence of charge 3 plus the force on charge 2 due to the presence of charge 1. So here's the formula. The total force is equal to the force on charge 2 due to the presence of charge 1 plus the force on charge 2 due to the presence of charge 3. So here's the formula, for the Coulomb's law formula. The electrostatic force is equal to K times Qn times Qn all divided by R squared. I represented Q1 and Q2 with Qn this time because since we're dealing with more than one charge, right, like charge 1, charge 2, and charge 3, I didn't want to confuse you guys with just like the rigid notation of 1 and 2, so I felt this was a little bit better. So yeah. Alright, let's make sure to convert. So we would convert 12 microcoulombs for negative, or for Q1 into 12 times 10 to the minus 6 coulombs, and for Q2 18 microcoulombs into 18 times 10 to the minus 6 coulombs. Before I proceed, you guys might be wondering, why did I just put in 12 and 18? Why not negative 12 and negative 18 as shown by right here? So since we're just calculating the magnitude as symbolized by these two vertical bars, we're just calculating the magnitude, right? We don't want the actual direction of this vector. We just want the magnitude, right? So we're just going to neglect those signs for now. Okay? So let's plug in everything we know. So K is 9 times 10 to the 9 newtons 7 meters squared divided by Coulomb squared, which is the Coulomb's constant. Q, in this case, that would be Q1, which is 12 times 10 to the minus 6 coulombs, and Q2 is 18 times 10 to the minus 6 coulombs. And R would be 4.1 meters, since Q1 and Q2 are separated by about 4.1 meters. Alright, so simplifying this a little bit more, 12 times 10 to the minus 6 coulombs times 18 times 10 to the minus 6 coulombs yields 2.16 times 10 to the minus 10 coulombs squared. And squaring 4.1 meters in the denominator yields 16.81 meters squared. As we can see, the meter square and the Coulomb square cancel out as they're both in the numerator and denominator of this problem. So now we're just left with the Newton, which is good because that's what the electrostatic force is measured in. So this problem just simplifies to 9 times 10 to the 9 newtons times 2.16 times 10 to the minus 10 all the way by 16.81 is equal to the magnitude of the force on charge 2 due to the presence of charge 1. And equating that will be, equating that in our scientific calculator will yield a value of 0.116 newtons. And that's just the magnitude. But if we were to write this in its vector form, right, as denoted by this arrow right here, to symbolize that we're writing in a vector form. So the blue arrow, right, or the force on charge 2 due to the presence of charge 1, since Q2 is being repelled in the positive vector direction, right, it's going towards the right, or the positive vector direction, we would symbolize this with an X in the positive X direction, as denoted by this little hat or arrow. If it was negative, we would just put a negative in front of the negative 0.116 to indicate that it was going the negative X direction. But in this case, it's going the positive, so 0.116 newtons in the positive X direction. That's the force vector on charge 2 due to the presence of charge 1. All right, now let's worry about the magnitude of charge 2 due to the presence of charge 3. So let's plug in everything we know. So K as usual is 9 times 10 to the 9 newtons times meter squared divided by Coulomb squared. In this case, we're plugging in Q2 and Q3, right? So in this case, Q2 is 18 times 10 to the minus 6 coulombs, and Q3 is 24 times 10 to the minus 6 coulombs. And remember, we had to convert them from microcoulombs, or from microcoulombs to coulombs, which is multiplying by 10 to the minus 6. And we're just plugging in, we're just finding the magnitude, so we don't have to put in their negative signs, as shown in Q2 with the negative 18 microcoulombs. So, and R is the distance between Q2 and Q3, which is 3.8 meters. So we'll plug that in as R. Simplifying this a little bit, 18 times 10 to the minus 6 coulombs by 24 times 10 to the minus 6 coulombs yields 4.32 times 10 to the minus 10 coulombs squared, and 3.8 meters squared yields 14.44 meters squared. Once again, meters squared and coulombs squared cancel out, as they're both the numerator and denominator of this problem. So now we're just left with the Newton, or N, which is the unit we want, and in the end is the unit not gravitational force, but electrostatic force is measured in this case. So the magnitude on charge 2 due to the presence of charge 3 just simplifies to 9 times 10 to the 9 newtons times 4.32 times 10 to the minus 10, all divided by 14.44, and plugging this into our scientific calculator should yield a value of 0.269 newtons as a magnitude, but in the vector notation, since once again the force on charge 2 due to the presence of charge 3 is Q2, in which Q2 is being attracted towards Q3 in the positive X direction, right? That would be in the positive X direction, right? So as shown as X and a little hat above. And once again, if it was negative, there would be a negative in front of 0.269 to indicate that it was in the negative X direction, but in this case, just positive X direction, so we just keep it as positive 0.269 newtons in the positive X direction. Alright, so now we can just find the net force, right? So what did we say the net force was? The net force is the total force, right? So that's going to be the force on charge 2 due to the presence of charge 1 plus the force on charge 2 due to the presence of charge 3, right? Because we're finding the net electrostatic force on charge 2, right? So we're combining the forces that act on charge 2, right? So here we can just, since there's only one component involved, which is the x component, we can just directly add them up. So we'll add 0.116 newtons in the positive x direction plus 0.269 newtons in the positive x direction to yield a value of 0.385 newtons in the positive x direction, as shown here. So once again, this is in the positive x direction, since we're adding two vectors that are in the positive x direction, right, towards the right, so they'll just add up to 0.385 newtons in the positive x direction. So, yes, that's how we solve this problem. Alright, we're going to do another one, and this is a little bit more challenging, so I would recommend please pause this video when you need to like, keep track and make sure you're understanding it, because it's kind of more complex and requires you to apply your knowledge of vectors and vector components and trigonometry, so let's get started. So number 6, calculate the net electrostatic force on charge 1 due to the presence of charge 2 and charge 3. Alright, so in this problem we're dealing with, so we're given that there's 3 charges, right? Charge 1, charge 2, and charge 3. We're finding the net electrostatic force on charge 1 due to the presence of charge 2 and charge 3. Okay? So here are the steps we should follow to successfully solve this problem. So step 1, draw and label everything you can deduct from the problem, okay? So here's the key. So I would recommend pausing this video after I present this key so you actually memorize this and keep this in your mind as you're watching the video, because this problem requires you to kind of know what's going on in the key. So, alright, so the red arrow is going to represent the x component of a force vector. The blue arrow is going to represent the y component of a force vector. The purple arrow is going to represent the resultant force vector. The black arrow is going to represent the direct forces acting on Q1, or charge 1. And the dashed arrows are going to represent additional vectors for abstraction. Alright, so let's start diagramming this out. So here are the 3 charges. Here's charge 1 with a magnitude of negative 9 microcoulombs. And its coordinate in space is point B, which is negative 1.5 comma 0. Here's Q2 or charge 2 with a magnitude of 7 microcoulombs and it's stationed at the origin. And here's Q3 with a magnitude of negative 8 microcoulombs and it's positioned at 0 comma 1.5. Alright, so here are the force vectors. These are just the direct forces acting on Q1, okay? So let's look at this. Alright, let's just worry about the red charge and the green charge, okay? So Q1 and Q3. So in this case, Q1, right, is negatively charged, and Q3 is also negatively charged, right? So what's going to happen to Q1? It's obviously going to be repelled, right? So in this case, Q1 is going to feel a force that's going to repel it in the opposite direction, right? So in this case, it's just going to go this way, right? It's going to go away. So we're going to be looking at them such that, like, they're in a, how do I say now, horizontal manner, right? So here's like if we were to just tilt these red and green charges, and we were to just rotate them in such that they're in a horizontal manner, then this charge would feel force that's repelling in this way, right? But in this case, since they're rotated, right here about this little rotation right here, theta, it's gonna feel force that's gonna repel it, right? So it's gonna go in this direction, right? It's gonna go anti-parallel right here, okay? And let's deal with the green and the yellow charges, right? So Q1 and Q2. So in this case, Q2 is positively charged, right? And Q1 is negatively charged. So Q1 is going to feel force that's going to attract it towards Q2, right? In the positive x direction, right? It's going to go towards the right, as denoted by these notations. So the force on charge 1 due to the presence of charge 2, and then the force on charge 1 due to the presence of charge 3. Alright, let's just draw these additional vectors for abstraction to create like a little right triangle. Alright, so here are the angle measures. So theta here is 45 and 45 degrees right here. So it forms like a 45, 45, 90 degree triangle. Alright, so here are the measurements. So between Q2 and Q3, they're separated by about 1.5 meters. Same between Q1 and Q2, and between Q1 and Q3, we could always use the Pythagorean theorem and just use a squared plus b squared equals c squared and solve. And we can also use our knowledge of the 45, 45, 90 degree triangle, in which we have a value of x, and x as the legs, and then the hypotenuse is x times root 2. So in this case, the hypotenuse, or the distance between Q3 and Q1, is 1.5 times the square root of 2 meters. Alright, so let's continue. So here's the tricky part. So here we're attempting to find the resultant force, okay? So that's this force right here. So essentially the resultant force, like I said, it's just a combination of the two forces, right? So that's a combination of this arrow and this arrow, right? So what we're going to do is we're going to end up drawing these arrows in such a manner that we can produce a resultant vector, right? So if we use the parallelogram method, we can project this vector to here and this one to here. And what we can do is we can draw a resultant vector from this point to this point, right? So from the initial points of both vectors to the terminal points of both vectors right here, as you can see, which is shown right here by this point and the total force, okay? Or we can also take this this vector right here, and then just translate it here, such that it's here, and then just draw an arrow from here to represent the resultant force. Alright, so now we just have to label the x components of the force vector. So in that case, we would just label this as these red arrows. So for the force on charge 2, the force on charge 1 due to the presence of charge 2, right? In this case, it's being obviously attracted towards Q2, right? It's going to feel force that's going to pull it towards the right in the positive x direction, right? And that's the only force that's acting on it, right? Or at least in relation to Q2. So that the only component it's going to have is the force on charge 1 due to the presence of charge 2. Okay? And here's the angle phi, which we'll find later on. And then here's the force on charge, here's the force on the x component of the force on charge 1 due to the presence of charge 3. And this red arrow, like I said, represents the force on charge 1 due to, or the force on charge 1 due to the presence of charge 2 in terms of its x component. And here's the y component of the force on charge 1 due to the presence of charge 3. And if you don't know what the components are, just think of them as like the x and y units I have to travel in order to reach a point where I can make a triangle, right? So think of like, if I have a 3, 4, 5 triangle, right? I have to travel 3 units to the right and 4 units up, and then I can form a hypotenuse of 5, right? So I had to go 3 units along the x-axis and 5 units along the y-axis to form that. Alright, so here's theta right here. Alright, so the second step is to calculate the electrostatic force acting on charge 1 due to charges 2 and 3. Calculate, and then step 3 is calculate the magnitude of the x and y components based off of the electrostatic forces you computed in step 2. Step 4 is add up the x and y components of each vector to find the x and y components of the resultant force. And step 5 is to calculate the resultant force's magnitude and the angle phi between the resultant force and the x-axis. Alright, so let's find the vector on charge 1 due to the presence of charge or the force. So here are they labeled. So let's remember to convert. So Q1 has a magnitude 9 microcoulombs, neglecting the negative sign. And Q2 has a magnitude 7 microcoulombs, so just multiply by 10 to the minus 6 to convert them. So plugging everything we know, we'll plug in K as 9 times 10 to the 9 newtons per meter squared, all divided by Coulomb squared. And Q1 is 9 times 10 to the negative 6 coulombs times 7 times 10 to the minus 6 coulombs, all divided by 1.5 meters squared, which is R. Then, as we can see, 9 times to the 9, or 9 times to the negative 6 coulombs times 7 times 10 to the minus 6 coulombs is equal to 6.3 times 10 to the minus 11 coulombs squared. And 1.5 meters squared is 2.25 meters squared. So meter squared and the meter squared, or meter squared and the Coulomb squared cancel out, as they're both the numerator and denominator of this problem. So with that said, we're just left with 9 times 10 to the 9 newtons times 6.3 times 10 to the minus 11, all divided by 2.25 is equal to the magnitude of the electrostatic force on charge 1 due to the presence of charge 2. And evaluating this should yield us a value of 0.252 newtons in the positive direction. And that's the case since, as we can see, so in the positive x direction, right? That's this direction right here, right? Q1 is being attracted to Q2, right? In the positive x direction, so towards the right. So the vector would just be in the positive x direction. And that would represent the x component, since there's no y component in this case. Alright, now let's deal with the force on charge 1 to the presence of charge 3. So here's Q1, here's Q2, and here's Q3. So like we said, Q1 is going to repel Q3 since they're like charges. And we can prove that the distance between 1.5 times the square root of 2, because 45, 45, 90 degree triangle, which leg equals x, leg equals x, and hypotenuse equals x times the square root of 2. So here it is, as shown. So we can just find the x and y component. So here's the red arrow, which represents the x component, and the blue arrow, which represents the y component of the force. So let's remember to convert 9 microcoulombs equals 9 times 10 to the minus 6 coulombs. 8 microcoulombs equals 8 times 10 to the minus 6 coulombs. Plugging these values in should yield the magnitude of force on charge 1 to the presence of charge 3 is equal to 9 times 10 to the 9 newtons per meter squared, all divided by Coulomb squared, times 9 times 10 to the 9, or 9 times 10 to the minus 6 coulombs times 8 times 10 to the minus 6 coulombs, all divided by 1.5 times square root of 2 meters squared. Continue. So the force on charge 1 due to the presence of charge 3 is equal to 9 times 10 to the 9 newtons per meter squared, all divided by Coulomb squared, times 7.2 times 10 to the minus 11 Coulomb squared, all divided by 4.5 meters squared. Meter squared and the Coulomb squared cancel out. They're both the numerator and denominator of this problem. And then we'll just be left with a value of 0.144 newtons in the positive x direction when we evaluate. Actually, it won't be in the positive x direction because we actually have to calculate the component. So this is just the magnitude as shown here. So Q1 has a magnitude of negative 13.2 microcoulombs. The force on charge 1 due to the presence of charge 2 equals 0.144 newtons. And they're separated by about 45 degrees, as shown here, the components. So yeah, we can prove that with the vertical angles theorem. And now, to compute the x and y components, we'll need to use trigonometry, so as shown here. So we can use SOHCAHTOA, and we'll use the cosine function. Cosine 45 degrees equals the force on charge, the x component of force on charge 1 due to the presence of charge 3, all divided by 0.144 newtons. Multiply 0.144 newtons to cancel it out, so they'll cancel on the right side, and we'll just be left with a value of negative 0.10182336 newtons, and we added the negative sign there because, as we can see, it's in the negative x direction, right? And the same thing we'll do for the y value, so as shown here. They cancel out, and we're left with the value of negative, we're actually left with the same value since it's a 45, 45, 90 degree triangle. It's the same value with the negative sign since the y component is in the negative x direction. Alright, so now to find the total force, we just plug in the x and y components that we calculated from the previous part of the problem. So we just add up the x components of the force, so 0.252 newtons plus negative 0.1018233376 newtons to yield the value 0.150176624 newtons. And for the y component, it's just, since there's no, for the force on charge 1 to the present charge here, there's no y component, so we're just left with this component right here of negative 0.1018233376 newtons. And plugging those values in, we'll get a magnitude of 0.181441501 newtons. So now we can actually plot that visually to represent it. So as shown here, we can see that here we'll produce a net force in the positive x direction, right? Since the positive x direction's magnitude of the total force is greater, as shown explained here. So here they are presented, and here's the total force, and here it is. And we can calculate phi, or the angle between them, by using the tangent function, and we should get a value of phi is equal to 34.14 newtons by taking the inverse tangent function, the y component over the x component, and the total force. And yes. And that's how you solve the problem. So we can express this as the total force is equal to this magnitude and negative 34.14 degrees relative to the x-axis, right? And then counter in the clockwise direction. So I hope this video helped you. And if it was confusing, please watch it again, go over the steps, because I explained it kind of fast. I had to go kind of fast on this. So I have good visuals, so please, if you need to take a time to look at it, please do so. And thank you for watching and have a great day.